Good afternoon, everyone. Today we are going to discuss about algorithm bits based on the previous questions given from the gate paper. What is the recurrence relation for the worst case of Heap Sort and what is the time complexity in its worst case? In general, we are going to find or arrange the elements in sorting order according to the Heap Sort by identifying the pivot element as the first element, and then we are going to arrange the elements.
Madam,
So
please
here,
share your screen, madam. Hello?
sir,
Madam, share your screen, madam. PPT share చేయరా
sir.
PPT, madam.
Sharing, sir. I'm sharing, sir.
Madam?
Is it visible, sir, now?
PPT share చేయరా
I have
No,
shared my
madam, not
screen, sir.
visible. Okay. Okay, madam. No, okay, madam. Yes. Now
Is
it
it
is visible, madam.
okay, sir? Thank you. So the recurrence
Madam, please
relation,
maximize your PPT. Madam, maximize your PPT, madam.
is it okay, sir?
మేడం స్టాప్ చేసి షేరింగ్ మళ్ళా ఆన్ చేయరా పీపీటీ కనిపించలేదు
Is it visible, sir, now?
ఓకే మేడం ఓకే
Okay.
థ్యాంక్ యూ మేడం
Thank you, sir. So here we have the options like recurrence relation T of n is T of n minus 2 plus order of n, and the time complexity is order of n square. And option B, recurrence is T of n equal to T of n minus 1 plus order of n, and with the time complexity of order of n square. When the worst case of quicksort occurs means when the picked pivot element is always occupying the last position in the given list, where we are going to have one element in one of the sublist and the other n minus 1 elements in the remaining sublist. In that case, the worst case of the quicksort occurs. So here in the worst case, quicksort recursively calls the subproblem with size 0 and the other subproblem with size n minus 1. So we are going to have the recurrence relation of T of n equal to T of n minus 1 plus order of n. So when we solve this recurrence relation using substitution method or either using Master's theorem method, we are going to have a time complexity of order of n square. So the worst case recurrence relation of the quicksort is T of n equal to T of n minus 1 plus order of n, and its time complexity is going to be order of n square. So the answer is option B. Suppose we have a order of n time algorithm that finds median of an unsorted array. Now consider a quicksort implementation where we first find median using the above algorithm. That means we are going to find the median of an unsorted array using order of n times, and then we use median as the pivot. Then what will be the worst case time complexity of this modified quicksort? So if we use the median as the pivot element, then the recurrence for all the cases it becomes T of n equal to 2 into T of n by 2 plus order of n. Whether we find the median as the pivot element or mean as the pivot element or the first element as the pivot element or whatever it may be, here the recurrence relation is going to be T of n equal to 2 into T of n by 2 plus order of n. So when we solve this recurrence relation using Master's method, so it comes under the case 2 of the Master's method. We have three cases for the Master's theorem method. So where we have a is less than b power d and a equal to b power d and a greater than b power d. So it comes under the second case. So if we solve that using Master's method, we are going to have the time complexity of order of n log n. So if we are going to find the median of an unsorted array using order of n time, we are going to have the time complexity of order of n log n. Now coming to the third one, given an unsorted array, the array has the property that every element in the array is at most k distance from its position in sorted array, where k is a positive integer smaller than size of the array. Which sorting algorithm can be easily modified for sorting this array, and what is the obtainable time complexity? So here, when we use the heap sort to sort the array, firstly create a minimum heap with first k plus 1 element and a separate array as the resultant array. So because elements are at most k distance apart from the original position, so it is guaranteed that the smallest element will be in the k plus 1 element. So now we are going to remove the smallest element from the minimum heap and we can extract the minimum element and again put it in the resultant array. Now insert another element from the unsorted array into the minimum heap. Now the second smallest element will be in this. So we are going to extract the minimum and continue this process until no elements in the unsorted array. So we are going to finally use the simple heap sort for the remaining elements. So in this case, we are going to have the time complexity order of k to build the initial minimum heap. So minimum heap for constructing the minimum heap, initially it is going to take order of k time and then it is going to take order of n minus k into log k for the remaining elements and order of 1 for the extracting minimum. So it is overall order of k plus order of n minus k into log k plus order of 1. So in that case, we are going to have order of n log k. So with the heap sort, by using minimum heap, we are going to have the time complexity of order of n log k. So the answer is option B. Now what is the time complexity of the given function? So here some code has been given. What is the time complexity of this particular function? So a function with parameter n in count equal to 0. So here we have two for loops int I equal to n, I greater than 0 and I is I by 2. And for int j equal to 0, j less than I, j plus plus. And we are incrementing the count variable count equal to count plus 1 and we are returning the count. So how we are going to calculate the time complexity for a particular code means we can perform this in two ways by using the variable count which is initially 0 and at every time when we are going to execute a statement we are going to increment that count variable. And how many times that count variable gets incremented, depending on that, we are going to calculate the time complexity. And the other way is we can prepare a frequency table method. So in the frequency table method, we are going to have the first column, the given code, and the second column, it is going to have statement for execution, whether that particular statement is executable statement or not. If it is executable statement, we will put the 1. If not, we are going to put 0. And next, how many times that particular statement gets executed in that code. The frequency of that statement we have to enter. And then we are going to find the product of statement per execution and the frequency. And then finally, we are going to add all those values such that we are going to get the time complexity of the particular. So here, this we have two for loops, and the first for loop it is getting incremented when I equal to I by 2. So for an input integer n, the innermost statement of this function is executed following time. So that is n plus n by 2 plus n by 4 like that. So on up to 1. So the time complexity T of n can be written as T of n equal to order of n plus n by 2 plus n by 4 plus so on up to 1. So in this case, we are going to have the time complexity of order of n. So whenever we are going to find the two for loops in the given statement, we should not consider that the time complexity is going to be order of n into n, that is order of n square. So how many times that each inner loop and outer loop executes, depending on that, we have to decide the time complexity of the given code. So here it is going to have only order of n. So the option is C. So what is the time complexity of this particular function? So here also we have two for loops. So I equal to 0, I less than n, I plus plus, and for int j equal to I, j greater than 0 and j minus minus. So what is the time complexity of this particular function? So the time complexity can be calculated by counting number of times the expression count getting incremented, or the statement count equal to count plus 1 is executed. So the expression is executed here in this example is 0 plus 1 plus 2 plus 3 plus so on up to n minus 1 times. So it is a series of number that is 0 plus 1 plus 2 plus so on. So the time complexity is going to be n into n minus 1 by 2. So in this case, we are going to have the time complexity of order of n square. So theta of n square is the answer for this. Now, the recurrence relation capturing the optimal time of towers of Hane problem with n disk. So, what is towers of Hane problem is? So, we will be given some three towers, and we are going to have disks in the first tower, and we have to move those disks to the other tower by using intermediate tower. So, here we have to follow that we should not place smaller disk on the larger one, and at every time we have to move only one disk. So by following that rules, we have to move the n disk from one tower to the other tower. So what is the recurrence relation for this towers of Hane problem? So that is, it is going to be T of n equal to 2 into T of n minus 1 plus 1. Plus 1 in the sense we are moving each time one disk, and we are moving the remaining n minus 1 disk to other, and we are replacing its correct position the last disk. So it is going to be 2 into T of n minus 1 plus 1. So for towers of Hane problem, the recurrence relation for n disk is T of n equal to 2 into T of n minus 1 plus 1. So the answer is option D. Which of the following is not the order of n square? So we have given some values here. It is not in the order of n square. So by looking at the option B, it is n power 1.98 means nearly n power 2, but it is not n power 2 exactly 1.98. And here we have option 3, n cube by square root of n. So if we solve this, it is going to be on n power 2.5, which is higher than order of n square. So the remaining are approximately 2 order of n square, but the option C, which is going to be n power 2.5, so which is higher than n square. So it is not in the order of n square. Now, which of the given options provides the increasing order of asymptotic complexity of the functions? So we are given four functions and we have to arrange those functions in the increasing order of asymptotic complexity. So the smallest order is going to be log n, then n. First it is going to be constant, next n log n log n square, like that. So here if you see, if you observe the functions, except f3, all other are exponential, except n, the function f3. So f3 is definitely first in the output. Among remaining, n power 3 by 2 is the next. So now we have to compare f1 and f4. So when we apply log on both sides of these functions f1 and f4, so the order of growth is, for f1 it is going to be order of n, and for f4 it is going to be log n into log n. So theta of n has a higher growth than theta of log n into log n. So f of 1 grows faster than f4. So the option is, first we have f3, next we have n power 3 by f2, next n power log n, next 2 power n. So f3, f2, f4 and f1. So the answer is option A. What is the best time complexity of the bubble sort? So we are given the options n square, n log n, n into log n square. So the bubble sort is best if the input is in the sorting order. So if the input data is sorted in the same order as the expected output, then we will come across the best case, and this can be achieved by using one boolean variable. So this boolean variable is used to check whether the values are swapped at least once in the inner loop or not. So we are going to have to go through all the n elements in the given list. So in that case, we are going to have the best case time complexity is order of n. But whereas in the worst case, it is going to be order of n square. When the best case occurs for this bubble sort means, if the list is already in the sorting order, just we need to go through all the n elements once and there is no change in the output. The output is same as the input. So in that case, we are going to have only the time complexity of order of n. But whereas if the input data is not in the sorting order, then in that case, we are going to have order of n square. So best case time complexity of the bubble sort is order of n. And when it occurs means if the input data is already in the sorting order. Now, what is the worst case time complexity of insertion sort, where position of the data to be inserted is calculated using binary search? So worst case time complexity of the insertion sort. And we are going to place the element to be inserted using the binary search. So applying binary search to calculate the position of the data to be inserted does not reduce the time complexity of the insertion sort. So though you use the binary search to find the position of the element to be inserted, it does not change the time complexity of the insertion sort. So this is why, because insertion of the data at an appropriate position involves two steps. First, we are going to calculate the position, and then we are going to shift the data from the position calculated in the step 1, and we are moving one step right to create a gap, and then we are going to insert the data which we want to insert. So using binary search reduces the time complexity in step 1, that is in order to find the position from order of n to order of log n. But the time complexity in step 2, it still remains order of n only. So the overall complexity remains same. So that is for insertion sort, the time complexity is going to be order of n square. So though we use binary search to find the position of the element to be inserted, it is not going to affect on the bubble sort. So it is going to be order of n square. So the option is C. So what is the time complexity of the below function? So here we have given some code. We have given for loop, and next we have given while loop, and we are incrementing j. So what is the time complexity of this below function? So when we have the first look on this code, the time complexity seems to be order of n square. As we are having two loops, for loop and while loop, we think that it is going to be order of n square. But here, the variable j is not initialized for each value of the variable I. Variable j is not initialized for each value of the variable I. So the inner loop runs at most n times only. So we are going to have the time complexity of only order of n, not order of n square. So don't decide the time complexity of the given function whenever we are going to have two loops or three loops in the code. How many times that loop repeats, based on that we are going to have the time complexity. So in a competition, 4 different functions are observed. All the functions use a single for loop, and within the for loop, same set of statements are executed. Consider the following for loops. So we are given 4 options, 4 for loops. If n is the size of the input, which function is most efficient? Among the 4 for loops, n is the size of the input means which function is most efficient? So here, coming to the first for loop, so the I getting incremented by 1, and the second it is incremented by 2, and in third for loop it is multiplied by 2, and in the fourth it is I equal to I by 2. Time complexity of the first for loop is order of n. Every time it is getting incremented by 1. And the time complexity for the second for loop is order of n by 2, which is asymptotically order of n. And the time complexity for the third for loop is, it is going to be order of log n. And the fourth for loop, it does not terminate. So all the functions, if we consider which is the most efficient, means it's based on order of n, order of n by 2, order of n log n. So efficient in the sense which takes least time. So it is going to be order of n log n. So we will consider option C is the best case. So if the following statement log n factorial equal to theta of n log n are the both same, the question is. So whenever we consider this n factorial, log n factorial and n log n, whenever the value of the n is large, then both are going to be same. So for large value of n, log n factorial is going to be equal to n log n. So we can say that the statement is true. What is the time complexity of Floyd-Warshall algorithm to calculate all page shortest path in a graph with n vertices? So Floyd-Warshall algorithm, when we go through that algorithm, it is going to have 3 nested loops in order to calculate all page shortest path for the given graph with n vertices. So it is going to, each loop repeats for n times. So it is going to be order of n cube. So the option is theta of n cube, that is option D is the answer for time complexity of Floyd-Warshall algorithm for all page shortest path. In Heap Sort, for sorting n elements, the n by 4th smallest element is selected as pivot using an order of n times. What is the worst case time complexity of the Heap Sort? So here we are selecting the pivot element with order of n times, and the pivot element is n by 4th smallest element. So for the case where n by 5 elements are in one subset, P of n by 5 comparisons are needed. Here we are supposed to consider n by 4th smallest element as the pivot. So we can write the recurrence relation as P of n equal to P of n by 4 plus the remaining n by 4 elements, n minus n by 4 means that is 3 by 4th element. So P of n equal to P of n by 4 plus P of 3n by 4. And we are going to have order of n times to select the pivot, so plus order of n. So when we solve this recurrence relation, it is going to be order of n log n. So whatever the element rather than the worst case, the remaining cases, we are going to have the time complexity. For the Heap Sort is order of n log n. Again, consider the quicksort algorithm. Suppose there is a procedure for finding a pivot element which splits the list into 2 sublists, each of which contains at least 1/5 of the element, and let T of n be the number of comparisons required to sort an element. Then what is the recurrence relation in this case? So here the list splits by considering or by finding the position of the pivot. It splits the list into two sublists, each of which contains 1/5 of the elements and the other contains remaining 4/5 of the elements. So we are going to have T of n equal to T of n by 5 plus T of 4n by 5 and plus n in order to find the position of the pivot. So T of n equal to T of n by 5 plus T of 4n by 5 plus n is the recurrence relation for finding the or finding the number of comparisons required to sort the n elements. So option B is the answer. Which of the following sorting algorithms has the lowest worst case complexity? Lowest worst case complexity. So sort worst case complexity is order of n log n, where we are going to have we are going to divide the list into two sublists, and then again we are going to take the left sublist and again we are going to find the mid element and then we are going to divide it. So 2 into T of n by 2 plus n. If you solve that recurrence relation, we are going to have order of n log n. And for bubble sort, it is going to be order of n square. And for quick sort, also it is worst case is order of n square, best case is order of n log n. And for selection sort also it is order of n square. So compared to the remaining, merge sort is having the lowest worst case complexity of order of n log n. So in worst or best or average case, the merge sort is going to have order of n log n only. So it is the lowest worst case complexity among the four. Which of the following is an advantage of adjacency list representation over adjacency matrix representation of the graph? So adjacency list representation, if you go to represent the graph, what is the advantage of it compared to adjacency matrix? So in matrix representation, we are going to have rows and columns. So we are going to use two for loops and each loop repeats for n times. So we are going to have order of n square. So in adjacency list representation, we are going to have identify what is the adjacent vertex of a particular vertex. Then in that case, we are going to have order of b plus e for adjacency list representation. And adding a vertex in adjacency list representation is easier than adjacency matrix representation. Yes, we are going to add one more adjacent vertex to the vertex. So adding by linked list, adding a vertex is easy compared to adding a vertex in the matrix representation. So all the three cases are the advantages compared to adjacency matrix representation. So list in adjacency list, space is saved. Matrix requires more space, and matrix representation requires two for loops, so it is going to be order of v square or n square. And adding a vertex in the matrix representation is complex compared to adding a vertex in adjacency list. So these are all the advantages. So the option is all above. So the degree sequence of a simple graph is the sequence of the degrees of the nodes in the graph in decreasing order. Which of the following sequences cannot be the degree sequence of any graph? Which of the following sequences cannot be degree sequence of any graph? So here 4 degree sequences has been given. So when we try to draw a graph with these degree sequences, its sequence cannot be the degree sequence of a graph. So there are some rules that the odd vertices in the graph should be even, or even vertices should be even, degree sequence should be even, like that. So by following that, we can say that the option 2 and 4 is not applicable or cannot be the degree sequence of any graph. So we have one vertex with a degree 1 and one vertex with degree 1. So we have two vertices of degree 1, and which is not the correct degree sequence for a graph, that is for a single graph. So option 4 is not true. And in the second option, we have 4 vertices whose degree is 6 and 2 vertices with degree 3 and 2 vertices with degree 2. So that is also not possible degree sequence. Consider an undirected, uninvited graph G. Let a breadth first traversal of G be done, starting from a node R, and let D of R, U and D of R, V be the lengths of the shortest path from R to U and V respectively. If U is visited before V during the breadth first traversal, which of the following statements is correct? So here D of R, U and D of R, V will be both same if at all U and V are at the same level. Otherwise, D of R, U, the distance that is between U and R will be less compared to distance between R, V. So you can go for the option 6, D of U R, U is less than or equal to D of R, V. So the option C is the right answer. How many undirected graphs can be constructed out of a given set of n vertices? In an undirected graph, there can be a maximum of n into n minus 1 by 2 edges. So total number of undirected graphs with n vertices is n into n minus 1 by 2. So n into n minus 1 by 2 edges can be formed. So like that, the graphs that can be formed with n vertices is 2 power n into n minus 1 by 2. So number of undirected graphs with n vertices is 2 power n into n minus 1 by 2. So it is option B. Which of the following statements is are true for an undirected graph? Number of odd degree vertices is even. Sum of degrees of all vertices is even. So the statement B, number of odd degree vertices is even. It is true. Why? Because adding an edge always increases degree of two vertices by 1. Q is true. If you consider sum of degrees and subtract all even degrees, we get definitely an even number because every edge increases the sum of the degrees by 2. So total number of odd degree vertices will be compulsorily even. So here both P and Q are true. Now coming to the next one. Consider an undirected random graph of 8 vertices. The probability that there is an edge between a pair of vertices is 1 by 2. What is the expected number of unordered cycles of length 3? So a cycle of length 3 can be formed with 3 vertices. So there may be total 8 C3 ways to pick 3 vertices. So we have the probability that 8 C3 into and probability that there is an edge between a pair of vertices is 1 by 2. So 1 by 2 whole cube. So 8C3 into 1 by 2 whole cube. So you find the value of it. Now given an undirected graph G with E vertices and E edges, the sum of the degrees of all vertices is sum of degrees of all vertices is equal to 2 into edges. So it is going to be 2e. What is the maximum number of edges in an acyclic undirected graph with n vertices? So acyclic graph with the maximum number of edges is actually a spanning tree. So in the spanning tree, we are going to have the maximum number of edges is n minus 1. So the correct answer is n minus 1. The maximum number of edges in an acyclic graph with n vertices, that is n minus 1. So we will stop here. We can go through the remaining in the next class.